would like to suggest that I write down some problems from the book which many of you would have had access to, okay? And I would suggest that as we keep going, you try to do the problems. It is worth your while. I mean, the problems are not randomly chosen, so it is worth your while. They are either practice problems or they illustrate ideas which we have been discussing. So they are very useful. And Rajesh was mentioning that there is somebody doing a tutorial for the other math physics course. Somebody else. Okay? Maybe that person can help. I do not know, but I do not know who it is. Okay? So, in the last class, I defined the following concepts. Okay. Let me change my notation somewhat slightly. Instead of calling this F, let me call it pi. Homomorphisms. Again, G to G prime. Here the statement is that this is isomorphism is 1 to 1. We assumed always on to. Here we have on to, but we don't have the 1 to concept. And then we also defined automorphisms. And endomorphisms. Okay. So we have here, so this is A, B, C, D. Okay. So C is A, G equal to G prime, G prime is G, and D is B with G prime G. So the image and the domain are the same when we talk about automorphisms and endomorphisms. So last time I don't see Jean. She suggested that one of the fundamental properties, okay, namely if E prime are identities of G prime, then phi of E is equal to E prime. Okay. This is I will give a proof, okay, which was suggested by her here. Okay. So the remark is you need very little to do this. It must be in books, but she was the one who brought this up. The only thing you need is the following. Okay. We need the following. One, okay. Pi is an automorphism. Okay. Pi of G1 G2 is pi of G1 pi of G2. This is because pi is a, not I should say, is either a isomorphism or a homomorphism. Okay. So this group properties are respected by the map pi. Secondly, we need the fact that the identity has a property that this one is E prime G prime is always G prime. Okay. This is all we need to see that this relation should be true. Okay. And one can do the calculation this way. It's quite easy and nice. We use the fact that E squared is E. So we know that E is E squared, E, because it is identity. So we know this equation. Now let us apply pi on this. Okay. If I apply pi on this, you see that pi of E is pi of E but this is in G prime, and it has an inverse. Okay, so multiply by phi of E inverse on right. So if I multiply on right, this is the inverse of phi of E. So in any case I will get E prime here. So that will be equal to phi of E prime. But the property I mentioned there, so this property star, this is equal to phi of E by star. So we proved that phi of E is E prime. Okay. It's quite easy proof. So it's worth seeing that fact. Okay. All right. Now I want to give examples, okay, of isomorphisms and homomorphisms. By the way, you please feel free to interrupt me, there is no problem. Okay. So let me look. We saw A1 that if S is a permutation, okay, we saw that there is we can define a linear operator Ls on Cn by, right, for each permutation I define a linear operator on the n-dimensional complex vector space by saying LFS EI is E of Si, where the E's form an arbitrarily chosen basis, okay, where this one E1 of the En is some basis of Cn. Right? This, of course, there are many possible choices for the basis. For each you will get a linear operator, and then this extends by linearity to all of Cn. By taking complex linear combinations, since I know what happens on the basis, I know what happens on an arbitrary vector. Then we saw that LFS, L of t is L of St. So this L, which is mapping you, so call this group, okay, S prime of n. Okay. Now the mapping we have got here the map from L is taking you from Sn to S prime n. Okay. It takes S to LFS. From that equation there is an isomorphism. Okay. This is an easy example. Slightly more interesting, okay, is the following. Okay. If G is a group, okay, and G0 is in G, what I will do is define phi of G0, this phi of G0 is going to be a mapping from G to G. So the domain and the range of this mapping phi are the same, and what does it do? Takes G to G0 G0 inverse. Okay. We will prove now, quite easy actually. This is an automorphism what people call as an inner automorphism. For each element of the group G, this automorphism always exists. Okay. So, how do I prove it? 1. It is 1 to 1. The proof is easy because if suppose I have this equation G0 G0 inverse is equal to G0 G prime G0 inverse. I simply peel off the G0s by multiplying the inverses, then I will get immediately G equal to G prime. Right? So it is 1 to 1, it is on to, how will I prove it is on to? That means on to means that the image under this mapping is all a G. Does anyone have a idea? To get phi of G0 or something here, to find so let's write like this, given okay, G in G, find okay, say H in G such that phi of G0 H is equal to G. This is what we want to do, right? On to. So what is H? Exactly. So it's phi of G0. Exactly, nice. Set. Well, okay. Set H is G0 inverse G G0. This is certainly in G. Right? So it's no big deal. Thirdly, it is an automorphism, okay, preserves group properties. Again the proof is easy, that is we take phi of G0 G1, phi of G0 G2, we multiply it out G0 G1 G0 inverse G0 G2 G0 inverse, but we have the associativity, so the middle G0s cancel, so I can cancel this with this, so this is phi of G0 G1 G2. Okay. So this is a example of an inner automorphism. Okay. This is actually quite important, although it's very simple, it's quite important, because when one tries to see, if you are given a group, okay, one tries to see what kind of automorphisms what I can do on the group. Okay. The inner ones we know already are there, so we would like to factor them out and see what happens with the remaining ones. Okay. This kind of problem arises typically in quantum either quantum mechanics or in quantum field theory. For example, you might have the rotation group, okay, or the Euclidean group. Rotation group, I think you know. Okay, and we may want to include things like parity, time reversal, charge conjugation. Okay, on top of this, but as automorphism, that is, they should not change rotation. If I make a time reversal transformation, you should not change the characteristics of a rotation. Okay, so those are outer they are automorphisms, but we don't want them to be, they are not going to be inner. Okay, so to characterize this automorphisms which are not inner, you have to know what they are inner and how the remaining ones are positioned. This is not a trivial problem.
What is the inner bit in this definition of inner automorphism?
Inner is this, that the group element itself generates the automorphism by conjugation. That is the definition of inner. Now I will prove perhaps one of the most significant results for quantum mechanics, okay, which explains, or which is the core result for explaining the relationship between spin, half integral spin, and spatial rotations. Okay. So I will prove. So the third thing we want to prove is there is a 2-to-1 okay, homomorphism from SU2, I have defined this, to SO3, okay, onto okay, with plus minus u in SU2 having the same image in SO3. Okay. This is what I will prove. Okay. One thing you should notice, okay, this plus minus, note, this thing minus 1 0 0 minus 1 which is coming here is in SU2 because its determinant is unitary, of course, but its determinant is 1. Okay. But if you do this in SU3 with 3 minuses, it will not be in that group. Okay. So this is quite important. And this is nothing but it will correspond, this object here will correspond to 2 pi rotation. In a way we will explain. So this is precisely the ambiguity is coming from 2 pi rotation becoming minus 1 when you go into SU2. This SU2 is called the covering group or in fact the universal covering group. Of SO3. Covering you can sort of understand, see, it is like Riemann surfaces. If you have done Riemann surfaces, you have branched coverings of the complex plane. So this is like Riemann surface. The universal business is because, maybe you know, maybe not, this comes basically because that phrase is SU2 is, if you may not know it, if you don't know it I will come back later, simply connected. Do you know if you know what is simply connected? You know the meaning? Huh? Sorry? Somebody here seems to know. Yeah?
Is it that all elements of the group can be reached if you continuously deform
No, no,
First
no, no,
group is trivial.
no, no. It means that every closed loop can be cut with a fixed point.
Reduced to rho first.
It's like if you take a plane, if you take a closed loop, I can contract to a point smoothly. But if I remove a hole in the plane, remove a point from the plane, then that is not true because I can go around and the hole is right. So in this sense, this SU2 is simply connected. Okay, this is in fact the 3 sphere. This is the 3 sphere. This topologically, this I showed you. The 3 sphere S3. Sorry?
First fundamental group is
Pi 1, this is the first fundamental group, is trivial. Pi 1 is trivial. If you do pi 1, homotopy, do you know homotopy groups? No. First fundamental group is the first homotopy group, that is trivial, which is simply connectedness. Okay? They are all the same stateness. And so there is some deep reason for this. We will see much later that give me any Lie group, any group like this, any group, SO3, whatever it is, you can always find some simply connected covering group. There is a canonical construction, okay? And that simply connected covering group is called the universal covering group. From that you can get all avatars of this original group, okay, in some way. Okay? So this is quite important. In quantum mechanically, for reasons which Wigner explained, whatever be the classical symmetry group, when you go into quantum mechanical state space, Hilbert space, you are obliged to deal with this covering group. Okay? And the covering group is not the original group because 2-pi rotation is trivial in ordinary space. Okay? So you cannot see it in classical mechanics. There is no meaning to say 2-pi rotation is -1 classically. Okay? But that is not the case in quantum mechanics because you are dealing with wave Hilbert spaces. Okay? So in the Hilbert space you can change sign of a wave function or a vector state. It will not show up in the density matrix or expectation values. Okay? So there is some new structure that is emerging in quantum theory. So I will prove success here is the following. Maybe I should write here. There exists a map R, okay, from SU2 to 3 cross 3 real matrices such that R of U1, R of U2 is R of U1, U2. I will find this 3 by 3 matrix for you. 2, okay. R of U, okay. Okay, the map R is at least, okay, is into SO3, okay. That is R of U transpose R of U is 1. When I say 1, I mean 3 by 3 1. Okay. Determinant of R is 1. I will prove that 3. Okay. The map is onto SO3. At a technical level, you don't even have to prove this, okay, because of some topological properties. Once you have this, you can say immediately you get everything. But anyway, I will show it explicitly. Okay. Because to infer 3 from 2, you have to use some properties of topological spaces. But we would like to do everything explicitly algebraically. So we will not bother. We will not be bothered with topological issues for the moment. Okay. And finally, R of u is equal to R of v means, and is implied by v is plus minus u. Okay. So we will prove these properties one by one. Pieces of these properties you would have come across in quantum mechanics. Okay. Bit here and a bit there you would have come. Okay. I will put them together and give a coherent proof. Okay. And the coherent proof will then apply to other situations. For example, some of you may be doing particle physics. Okay. Then you have this business of 3-dimensional representation of quarks and 8-dimensional representation of gluons. You might have come across this. There is a relationship between the two, very much like SU2 with SO3. Okay. So we will see how that can be worked out along the same lines, and many other things like that. So let me start with proof of 1. So we have the list. Okay. 1. Okay. So let me remind you of some elementary properties of Pauli matrices. Okay. Let tau I equal to 1 to 2, 3, the Pauli matrices, the standard ones. Okay. So the tau is a Hermitian and they are traceless. Okay. So these are traceless Hermitian matrices. Also, okay, if M is any 2 cross 2 matrix, take an arbitrary 2 by 2 matrix, we know that this M, the space of 2 by 2 matrices is 4-dimensional, okay, over complex numbers. So I can write this as alpha 0 unit matrix plus summation I alpha I tau I. But this alpha mu or alpha lambda are some complex numbers. Okay. This is simply the statement that the space of 2 by 2 complex matrices form a 4-dimensional complex vector space. Now, if M is real, if M dagger is M, if M is Hermitian, from this equation you can see that alpha lambda are real, right? Because this tau is and 1 are linearly independent, and when you take complex conjugation, the coefficients will undergo a complex conjugation, and since the matrix does not change, these are real. If trace M is 0, then we know that alpha 0 is 0. Okay. So a traceless Hermitian matrix, this is the important point. M 2 cross 2 first can be written as M as summation alpha I tau I alpha I real. So the space of traceless Hermitian matrices is a 3-dimensional real vector space. Okay. This is what this is, which is like your R3. In fact, the space of 3-dimensional space of 2 by 2, sorry, I am saying the wrong thing. The space of 2 by 2 matrices which are traceless Hermitian is a 3-dimensional real vector space, and this isomorphic to your is the same as up to basis change as your ordinary 3-dimensional real vector space. Okay. Now consider for u in SU2 this object, okay, tau I prime, this is u tau I u dagger. U is a 2 by 2 matrix which is unitary and has determinant +1. From here you see the trace of tau I prime is 0 because of the cyclicity of the trace. We can write inverse here. It is Hermitian. Because when I take Hermitian conjugation, it does not change. So I know that this object here is a real linear combination of the original Pauli matrices. So I write this is a real linear combination. So I write this as summation j tau j, some matrix here, some coefficients of the linear combination. But these coefficients certainly will depend on I and it will also depend on u, right. So this is simply that result where the dependence of this vector on I and the fact that when I construct this tau I prime I have used this view have been exhibited. Now this equation, okay, determines this R J I U uniquely because tau I are linearly independent. Yes, there is another, I mean, suppose there is another solution R prime, you equate them, but the taus are linearly dependent, so the coefficients must be equal. So we have a uniquely determined, so okay, we have a map, okay, right, R. This is notice that this is 3 by 3 matrix from U to 3 cross 3 real matrices R of U, right. I determine a 3 by 3 matrix uniquely from the given U. Now it is this R we have to understand, this mapping we have to understand. So let me see what happens. I want to prove this second result here. Okay, that's also easy. Okay. So all that I have to do is now U1, U2, tau I, U2 dagger, U1 dagger. U1 and U2 are unitary elements of SU2 for UI and SU2. I do it first successively. First I work this out. This is equal to gives, okay, first is U1, I get tau j R j I of U2 U1 dagger, and I apply it again. So it's tau k R k j of U1 R j I of U2 but this is simply matrix multiplication. So this is equal to tau k r k I should be careful, r of u1, r of u2, ki, but I can also think of this as u1 u2 as one unit, tau I u1 u2 adjoint. So by the same, and this is again in SU2, so I can apply the same formula and you find that this is tau k r k I of u1 u2. Comparing this with this, we prove that r of u1, r of u2 is r of u1 u2. Yes. So I have proved the first part of the statements I have made. Now I want to prove the second. So to prove two, I will use some identities involving Pauli matrices. Some of you may know that this Pauli matrix is from something called Clifford algebras, okay? Maybe those are, but anyway, we have tau I tau j. Do you know how to expand this in taus? It is a famous formula, yeah? Yeah, you know it, yeah? Exactly. So this delta ij 1 plus I times epsilon ijk tau k. Good. Okay. I will use this formula, okay, to get the answer. Okay. So apply u right hand side, u dagger, so yeah, so this will give me delta ij 1 first for the first term, where u dagger is 1, and for the second term plus I epsilon ijk, okay, let me call it tau L r L j of u. But this is also u left hand side u dagger. So what I will do is u tau I u dagger, u tau j u dagger. Okay. So I apply, I am going to get some quadratic relation in R's, which is good. Let us work it out. This is tau k r k I of u, tau L r L j of u. Okay. Now I can again apply the Pauli matrix formula. Okay. So this is going to be tau k, well, r k I of u, r L j of u times delta k L 1 plus this 1 is 2 by 2 1 plus I epsilon k L m tau m. Right. So this is equal to this. So comparing the two, first equation I get is something very promising, delta KL, and that is equal to this expression here. So you will find that R of u transpose R of u is equal to 1. Okay. So this implies R is 3 by 3 real and is orthogonal. So we know that R of u belongs to O3. The second one says that I am trying to see, okay, it is saying that R L J epsilon I J K, right? I hope I got the indices right. I think this index, let me see. Let me see on the right hand side. So here ijk, it should be k, no? It should be k. Right? Because I am rotating this object, this thing here, right? So it should be k. So I got this is equal to the other one RKI. Well, I am omitting the u here, but RLJ times epsilon KL. The m should match. So here it is. I am not very happy with the indices. This is not a major point, but how will I choose my index? IJL, let me see. This is tau m. Here I am comparing with the index L. So I can change L to m. So let me change this L to m. Then I will write epsilon LKM. Let us see whether indices match. Okay. IJM, IJM. Okay. Now I want to peel off this R and put it on the other side. So what I will do is multiply this by R m something, some index n of course u, and use R transpose R equal to 1. So this one will give me delta Kn because of orthogonality. So this will become epsilon, can you see? I hope you can see. IJM, IJ summing in n, so I get n, delta Kn, I get n, is equal to R K I R L J R M N acting on epsilon K L M. Okay. What does it mean? Let us I J N. What does this equation mean? These are of course arguments is u. This is something you know, you should know. This is something on R. I am multiplying 3 R's and totally anti-symmetrizing with epsilon, and I get back the epsilon. What is it? Huh? It's a determinant. So this is saying that the determinant of R of u is 1. Right? This is the equation which defines the determinant. Okay. So this proves, or determinant of R of u is equal to 1. Yes. So what I have proved is or R of u is belonging to SO3. Yes. So I come up to this point. I come up to this point. Right? I have proved that there is a homomorphism from SU2 to SO3, and I found you the matrix, 3×3 matrix corresponding to each element of SU2. Okay. I want to prove this part, that every rotation can be obtained this way. So I want to prove this item 3. So what I will do is, let S be a rotation, SO3. Okay. Then by Euler's theorem, I can write S as S3 gamma, S2 beta, S3 alpha, okay, where say Sj some delta is rotation by delta, angle delta around axis j. Yes, I think you know this result, no? If you have ever had to suffer through learning spinning tops, you would have come across this. Okay? There are few things I heartily dislike. One of them is this Euler angle. But anyway, there it is. It's best if you are doing any real calculations. If it can be done at all, it can be done without Euler angles. Okay? For sure. Including spinning tops. I have done it. Okay? Can be done. If you look at the books of the masters, Felix Klein or somebody, you will not find a trace of Euler angles. Okay? So it is just the Goldstein, some kind of test by fire, like Sita. But anyway, here it is simplifies the proof. Okay? So what I will do is, okay, we will find U3 of, in this case, what is the angle here, of alpha, such that R of U3 alpha is S3 alpha. This I will find explicitly to see how it works. Okay. Once I know this, similarly, R of remaining things, okay, for the other two things, okay, namely U2 of beta is S2 beta, etc. Okay. This actually proves the result. Why? It is enough to show this, to show that R is the mapping is onto. Why? What I have to show is that I can get any S this way, but if I show it for the 3 special rotations, I have done finished the calculation. Why? Because then S is what? I use the homomorphism property. I will simply write R of U3 of gamma, U2 of beta, right, U3 of alpha, by the homomorphism property, because I can apply R on each, as R is a homomorphism. So I have to show this result only for one of these special rotations. Now S3 of alpha, so 3 by 3 matrix, and the equation is cos alpha sin alpha minus sin alpha cos alpha zero zero 0 0 1. Okay. What I have to do is, okay, so to find, well, U3 alpha such that you want U3 alpha tau 1 U3 alpha dagger, okay, will be rotating this tau by the first column, so it will be cos alpha tau 1, okay, minus sin alpha tau 2 because this is tau j S3 J1, for tau 2 same thing will be sin alpha tau 1 plus cos alpha tau 2. For tau 3 it will not change. Okay. This is what, so we want to find this U3 with this property. The calculation is simple. I will finish this proof here. So maybe I will take a couple of minutes extra. Try U3 alpha is exponential I tau 3 over 2 alpha. This half is very important. The significance of this half will dawn on you more and more as you keep living. So let me try U3 alpha tau 1 U3 alpha dagger is what? This is cos alpha over 2, right, plus I tau 3 sin alpha over 2, right. From here my power series is expanding and using that tau 3 squared is 1, you get this formula times the tau 1 in the middle times the inverse of this, which is cos alpha over 2 minus I tau 3 sin alpha over 2. Let us see whether we get that formula. Let us simplify. First I multiply by tau 1 is equal to tau 1 cos alpha over 2 plus I tau 3 tau 1 is I tau 2 sin alpha over 2 multiplying cos alpha over 2 minus I tau 3 sin alpha over 2. Now this is minus tau 2, so let me expand this out, okay. So this is equal to better visual. Yes, yes. So this is tau 1 cos alpha over 2 minus tau 2 sin alpha over 2 times cos alpha over 2 plus I tau 3 sin alpha over 2. Okay. So the formula I want is that first line, okay. So let us connect tau, so this one is equal to tau 1 coefficients, one is cos squared alpha over 2 from here, then there is another tau 2, this term, okay. Tau 2 tau 3 is I am.
That should be minus I tau.
Sorry? There should be a minus here, right? I was worried. I was getting the sign wrong, so that's why I hesitated. So tau 2, tau 3 is I tau 1 by cyclic thing. So get I tau 1 plus I, so get minus sin squared alpha over 2. Then you have to worry about the cross terms here. Okay. So let me, the sign we want is minus tau 2. Okay. Then you get sin alpha over 2, cos alpha over 2. Then this term here in minus, but tau 1, tau 3 the wrong order. So if you adjust the order, you simply get the factor 2. Okay. So this is exactly cos alpha tau 1 minus sin alpha tau 2. Okay. So this is okay. Okay. And similarly, rest. You get the remaining equations in exactly the same way. So I have proved quite explicitly that the mapping is onto SO3, and I actually given you a rule for finding the elements in SU2 which map to the same element in SO3. I have given you explicit formula. And so I will finish off this today by looking at this last part. Okay. Last part is since u tau y, u dagger is tau j r j I of u. By the way, you should notice the way the indices are summed. If you put the summation on the other side, suppose you put r on this side and sum, okay, you will get the wrong answer. You will find ru rv is r of vu. You will get the what they call opposite representation, which you don't want. So you have to put it on this side. It's clear. Okay. From here itself, you see that r of plus minus r of u is r of minus u. That's obvious, because the minus 1 doesn't do anything. Also, you want to prove that this is there are nothing else that can happen. You want to prove r of u is equal to r of v, implies you want to prove that v is minus u or plus u. How will I do it? And this v there, you see that this says that v dagger u commutes with tau I. Okay, but for sure v dagger u commutes with 1. So v dagger u commutes with all two weighted matrices. Okay, so v dagger u m is 0 all m. Yes. So what can I say about m v dagger u? What is the matrix which commutes with every matrix? Huh? It's a multiple of the identity. Okay? So all that can be is alpha 0 times 1. From this I can infer what I want. What will I do? I want to show that alpha 0 is plus minus 1. What will I do? Take determinant. Okay. This determinant here, this notice that this is alpha 0, alpha 0. Like so. So take determinant. You get 1 is equal to alpha 0 square. Or alpha 0 is plus minus 1. Right? So I have proved the last item here in the proof, the calculations. So we find that this SU2, there is a 2-1 homomorphism from SU2 on to SO3, so that for every spatial rotation I can assign in SU2 two possibilities. They differ from each other by a 2 pi rotation. Okay. This is the only difference between them. They differ from each other by a 2 pi rotation. In fact, you cannot individuate one of them. I mean, you have two possibilities, but if you try to fix one of them uniquely always, you cannot do it for topological reasons. So what you have got here is, for every rotation, which I called S, you have two U's, U and two U's, U1 and U2. Both give you the same rotation. They differ by a sign. Okay. You can say they differ by a sign, but can you fix one of them uniquely? No, you cannot. Okay. I mean, it is not possible to say that therefore I will pick one branch and throw away the rest. You cannot do it, because like in Riemann surface, if you go around somewhere, come back, you will find that this sign has changed. Okay. So this is what we have proved. Okay. And this is, as I say, somehow at the core of much of quantum mechanics when you deal with spin half. Okay. So we have to understand that quite well. Okay. So next class, that is tomorrow, I will start doing subgroups. Okay, I will give several examples, and then we will go into this really important aspect of cosets and invariant subgroups and factor groups. Okay. This is conceptually it is at slightly higher level, but again they play a very fundamental role in many things that we do. So that is what I will do. Okay. Subgroups, I will give you a bunch of examples. Okay. Some of them may be surprising, some may be obvious, but some are obvious, some are not so obvious. So we will see how it works. Then we will go into these cosets and invariant subgroups.